Learning targets for acids and bases and redox reactions. This is still currently Unit 4. Basically looking at properties and changing substances and chemical equations and reactions here. That's kind of the overall arching theme, that first one for the entire unit. But today we're specifically looking at acids and bases, so we're going to define them with the Arrhenius Bronsted-Lowry different definitions and how they represent their acids and bases. We're going to determine conjugate acid-base pairs, write net ionic equations for acid-base and redox reactions, calculate quantities using stoichiometry. Of course, here comes the math component. Identify terms to describe and look at titration, and identify oxidation numbers for elements in a reaction. So there's our learning targets for this particular set of notes. Now, the Arrhenius acid definition and Arrhenius base definition, they're the most basic of definitions for acids and bases. Learned this one in Chem 1, same kind of idea here, where an acid is any species that produces hydrogen ions in solution. Now we're going to kind of alter that. I know it was represented probably last year as well as in some respects as hydronium, but we're going to be looking at the hydronium representation. Okay, so basically it's just the ion, the proton attaches itself to water, and then you end up with your hydronium ion, this H3O+. And we'll talk about hydronium in a little bit more detail in just a minute. So hydrogen, hydronium in solution, are you making these ions? Base, of course, is very narrow. It's only talking about hydroxide ions in solution, so that's only a small realm of different things that can produce hydroxide in solution, because most of your hydroxides we know are insoluble or they precipitate out. So there's, your alkali metals, your like KOH, LiOH, alkali metals, these are all strong where they produce hydroxide in solution. You have your alkaline earth metals, the heavy ones that are considered strong too. Strontium, barium, calcium, strontium, barium. These ones are considered strong as well. The rest of the alkali metals too, like rubidium hydroxide, although we don't really use rubidium or cesium hydroxide either, because they're getting into super heavy metals. We basically stick to these three if we're doing stuff with hydroxide. These would be the ones that we would consider Arrhenius bases because they produce hydroxide in solution. Now, Bronsted-Lowry definition talks about being proton donors and proton acceptors. Essentially, what is an H+? Well, hydrogen only has one proton and one electron to begin with. So if H becomes H+, that means it lost an electron came off. So really, we're talking about a single proton. So that's why we call them proton donors, proton acceptors when we're talking about hydrogen ion, hydrogen cation. Bases are proton acceptors, of course, so they would be accepting the hydrogen. Now, the way we kind of set this up, we have our generalized acid, which would be HA. In this case, the water is going to act as a base because it's going to be the one that accepts the hydrogen. The hydrogen is going to come over here. In that particular case, water is a species that can act as an acid or base under the Bronsted-Lowry definition. It can accept a proton, it can donate a proton. So looking at this particular scenario, we say that's amphoteric, a species that's capable of accepting an H and also donating an H. There are other ones, and we'll get into more detail, but like dihydrogen phosphate, okay? That particular one, obviously you can donate and you can add a hydrogen to it because you can make a phosphoric acid. So you could also take away a hydrogen from it and it would be not dihydrogen phosphate anymore, it would be hydrogen phosphate. So there's lots of species out there, and we'll examine them more when we get to Unit 8 when we're into all of the weak acid base equilibrium stuff. But just a general idea here, so that this H donates it over here, that's why we get hydronium, because it's now gained a hydrogen. And of course the HA, it loses its H, so it becomes A- or the anion on the other side. Now going back to looking at hydronium, we do use them interchangeably. H3O plus equals H plus. So if you see it written as H plus or you see it written as H3O plus, when you see either designation, you should think acid automatically. But here's a little bit more detail showing the Lewis structure. You see the lone pair at the top, the brackets +1 means it has one less electron than it does proton in the configuration of the entire compound there. Of that polyatomic ion, it is tetrahedral for the electron domain. For the molecular geometry, though, it happens to be pyramidal shape. Okay. So definitely start identifying, and when you see hydronium, you would know that that's representing an acid. So let's look at the conjugate acid-base concept here. So this particular one, once again, using our HA example, it's going to give away, here's our hydrogen, here's our anion. It's going to give away to the water over here, and the water's acting as a base because it's going to accept the hydrogen. And we get hydronium over here, and then we get the A- that's missing the hydrogen. The acid and base are always in the reactants. So over here in the reactant side, always going to be designated as the acid or the base. Over here on the product side, this is where you find your conjugates. Conjugate acid, conjugate base. Now, what designates each one? A conjugate base is everything that remains of the acid molecule after the proton is lost. So if you look at the original acid, right here, the original acid, it's now missing an H. Well, what else was in the original acid? A-. So A- over here, that's your conjugate base on the product side. The conjugate acid, of course, is formed when the proton is transferred to the base. So if we're looking at our original base, in this case, the original base was water. We're looking for like H2O with an additional hydrogen. Well, that happens to be hydronium. So hydronium turns into the conjugate acid. The conjugates are always on the product side. The acid-base labels are always on the reactant side. Now let's look at how these are represented in different equation form. If we're talking about an Arrhenius acid, once again, most of the time you're looking at hydrogen ions in solution in water. That's the basic definition. So when we look at these, we're looking at just dissociating them into their ions. So H plus, AQ designating it's dissolved in water, and then Cl minus. So just break it up into its ions when we're looking at from a Arrhenius particular view of the equation. All right, just break it up. This is a strong acid. It's going to completely dissociate anyways. We completely just break it up into its separate ions and can designate it that way. However, if we want to represent it more in the Bronsted-Lowry fashion, using that definition, this is where you would take your acid, and of course you would react it with water, and water would be the other substance in the reaction. Because we have our proton donor, I'm going to change colors real quick here, because that's, we'll go with green. Oops, didn't mean to do that. Oh, come on. Okay, here we go. We have our H here, and that's going to transfer over to our water. So here is our Bronsted-Lowry acid, the proton donor. Here's our Bronsted-Lowry base. In that case, then this becomes chloride over here because it lost its hydrogen. And then over here, the water gained the hydrogen, so it becomes hydronium. And then over here, looking at the conjugate acids now, this was the acid, it's lost its hydrogen, this becomes the conjugate base. This was the base, it has now become the acid by adding the hydrogen, so it's now the conjugate acid over here. So the main difference, as you see when we're representing it in terms of the Bronsted-Lowry, is we have the water also there because you have to have an acceptor of the proton as well as the donor of the proton, where in the Arrhenius fashion, or looking at that particular reaction, you just break it up into its two ions. And there you have it. Now, before we get into the ammonia as both Arrhenius and Bronsted-Lowry, ammonia is a weak base, and we'll talk more about the weak idea later on when we get to Unit 8. But if we were just looking at a regular, strong acid, say KOH, I'm not not acid, I mean base, KOH, potassium hydroxide. And we're going to, show the reaction here. Well, once again, if you were just doing Arrhenius for a strong, it would just break up like this into its ions, and you would get potassium ions and you would get hydroxide ions. You would just break it up and dissociate it like normal. Ammonia, though, however, is a weak base, so we can't really represent it that way. You have to show it in water here, okay? Here's the water. Now, the ammonia is going to be acting as the base. So that means the water in this case is going to act as the acid. And this is showing it from the Bronsted-Lowry fashion. This H is, of course, going to transfer over. So that makes us end up adding an H to our ammonia, which turns into ammonium. Now, whenever you add an H plus to anything, that's going to add one to the charge. Because you're adding a positive, you're adding a proton, so you're always going to add. Now, if you take away a proton, it's always going to subtract one from the charge. So here that I take away a proton, so that what's left from my water, well, only the OH is left, and it gets a -1 because I took away one of the positives. So here we get AQ, of course, AQ. Now, why does this also represent the Arrhenius definition? By the definition, it's supposed to produce hydroxide in solution. If you look here, hydroxide was produced. It is a product. So technically, it could fit that definition. Very few, arrangements here in terms of the bases here that, like I said, it's always the strong ones, the hydroxides in the alkali metal group, and then the alkaline earth metal, calcium, strontium, barium hydroxides. Those ones, of course, also fit the Arrhenius definition. And then this case where you have the transfer, where it rips off a proton off of the water and it creates hydroxide, it also can fall under that particular definition. And then the Bronsted-Lowry one, here is your acceptor. And here's your donor. So we can also describe it based off of the Bronsted-Lowry definition. Of course, this one becomes the conjugate acid because now it has the hydrogen attached. And then over here would be the conjugate base for the hydroxide because it's the one that lost the hydrogen. The acid becomes the conjugate base. The base becomes the conjugate acid. Now, here's an example where we're not looking at it with water or with hydroxide being represented at all. And we can describe this reaction as a Bronsted-Lowry base idea here. Now, the double arrow in the middle is indicating an equilibrium position, and so we'll get more into these weak. This has like the weak idea here where the phosphate's acting as a weak base. We'll get more into that equilibrium position stuff later on once we've covered equilibrium, and that's why I said Unit 8 is going to be more about the weak acid base equilibrium information. But here, looking at the phosphate, we have nitric acid. So the H obviously here is going to have to be the one that donates, and the phosphate's going to be the acceptor. So in this case, this is going to be acting as the base. Obviously, nitric acid is your acid. Over here, the nitrate becomes what? Which one is it? The conjugate acid or the conjugate base? Yeah, this is the conjugate base because it lost its hydrogen, so now it becomes the conjugate base. And then hydrogen phosphate over here becomes the conjugate acid. But this one shows there's no hydroxide being produced anywhere, so you would not consider phosphate to be an Arrhenius base because it's not producing hydroxide in this particular reaction. You would only label it a Bronsted-Lowry base. Okay, so that's a good example there showing it how it can meet the one definition without meeting the other definition in terms of the description there. All right, neutralization, because that's the main reactions we're going to be looking at this particular junction of acids and bases. Neutralization. Neutralization, of course, is always the acid plus the base gives you water and a salt, which is in the term of an ionic compound. That's the generalized format for neutralization. Now, we're only looking at strong because strong doesn't have an equilibrium position. Strong goes to completion. Strong acid reacting with a strong base will always go to completion, and you won't have an equilibrium position to deal with. So the net ionic for a strong acid reacting with a strong base is always the hydrogen reacting with the hydroxide produces 1 mole of water. So that's always going to be the net ionic when they're talking about a strong acid reacting with a strong base. Like I said, weak is a totally different situation, and like I said, we'll look at that later. For right now, though, I want to show you the animation, which kind of shows you the particular model diagram. Very good representation here of figuring out what's doing what, and it going to look at the neutralization of the strong acid, strong base reaction. Okay, so describing the setup here before we begin, what you see is the bottom of the burette here, okay, has a little toggle switch so you can let out a certain amount of liquid or a solution into your flask or beaker down here. And usually what you have in the burette is your known solution, the one that you know the concentration of. You usually put the analyte, the one you're analyzing, into the flask or the beaker. And here I'm going to press play, and we'll take a look more on the molecular level now. Okay, so they removed the water, of course, to make it easier to see with just a few. They left in a few waters. Okay, showing you that this is the representation about a pH of 4. So this is a weak hydrochloric acid concentration going on. And obviously the hydrogens face inward because chloride is minus, showing that representation here. The hydronium, H3O plus here, is what outlined in blue. And of course, these Mickey Mouse ear ones are going to be the regular waters. Now, as it progresses through the animation, they're going to dump some sodium hydroxide in here, which would be the base. All right, so let's take a look at what happens here when it does that. Oh, in the meantime, yes, the H's can switch from water molecule to water molecule, but you see consistently there's still one hydronium floating around in there. All right, now the sodium hydroxide has been added. Same thing here, the H's can switch from the hydroxide. But that's where the neutralization just occurred. The hydronium and the hydroxide just combined between these two, and now we both have water molecules, which is neutral, of course. And you can see here on the sodium, the oxygen side face inward because the partial negative is attracting to the partial positive there. So that's what it would look like inside the beaker. So definitely make sure you're doing good analysis on looking at those particular model diagrams. I'm sure I'll find some good example ones to put in your problem set or, for review, because you always need to be able to interpret those diagrams for AP. Now we're going to start looking at performing acid-base calculations here. And this is going to involve the stoichiometry. And it's pretty basic stoichiometry, acid-base, neutralization reactions, definitely how much of this would need to react with this in order to, neutralize it completely, or if I react this with this, how much water would produce and what do we have in excess kind of thing. Same kind of questions that you've seen for regular stoichiometry problems and reactions. Definitely the best thing to always approach every problem is what species are there, what species are being made, give a good evaluation of that. Write out the balanced equation. At this point, we're definitely sticking with the molecular equations rather than looking at it from a net ionic perspective for strong. When we get to equilibrium weak stuff, we'll be looking more at the net ionic type reactions. You can always calculate the moles. Sometimes going to the moles takes longer. Sometimes going to the grams or whatever, like you can do it multiple different ways, but a good bet is to go to moles. They usually ask you to go to moles first. Let's go back to that. Sorry, didn't mean to hop forward. In AP, they usually have you calculate moles before you calculate anything else, but you can skip the moles if you don't need to go to the moles. Determining limiting reactant. So if you're given both reactants, you're given amounts of both reactants. You know it's going to be a limiting reactant problem where you have to work both. If you're only given the one and it says the other stuff's in excess, then you don't have to calculate both. Calculate moles or grams or whatever of the product that you need to calculate at the end there. So now we're looking at this particular one, exercise 1, what volume of a 0.1 HCl solution or hydrochloric acid solution is needed to neutralize this certain amount of the sodium hydroxide. Well, this turns into stoichiometry. So first things first, looking at what I have hydrochloric and I have sodium hydroxide. Any ideas where I should begin? All right, so we're definitely going to have to look at, I will look at volume because that's what it's asking about here, and I will definitely take that under consideration. But yeah, I probably should balance my equation first. So I'm going to go ahead and do that. I've got HCl as my first reactant, and it's in solution, so I can label it AQ. And neutralizing another solution, which is sodium hydroxide. Here, when I look at the products here, what's one of my products going to be? It's always one of the products of a neutralization reaction. Water, good. So water is going to be one of my product, and that's a liquid. And then the other one here, of course, we're looking at the spectators that would be involved because they don't participate in the reaction, is going to be the sodium chloride. And of course, they're soluble, so it would stay AQ in solution there. Now, balancing wise, most strong combinations are going to be 1-to-1 in terms of molar relationship. There are a few that you have to watch out for, like those heavy metal hydroxides like calcium, strontium, barium, because as you can see, this is 2 hydroxides per molecule. Barium as well. This one's one to look out for. And then occasionally you'll have some diprotic acids. Diprotic means 2 protons, like sulfuric, where there's 2 hydrogens in there. And then when you balance the equation, it ends up being like a 1-to-2 ratio rather than a 1-to-1. So watch out for those because sometimes they do pop up. Not everything is 1-to-1, but the majority of acid base are monoprotic with just a singular hydroxide. In this particular case, it would be monoprotic. Now, yes, looking here, what volume of 0.1 solution is needed to neutralize 25 milliliters of 0.35. Now you can use the molarity equation to find the moles to start with and then use the moles as the beginning of your T-chart. I think that takes longer. I don't think it's as beneficial to you than to just start and use the molarity as a conversion factor. So I know the amount I'm starting with in terms of volume. I know this concentration. I can start my track with this volume of our base. So 0.0250 liters. And yes, change it to liters. That's a very good suggestion. You could put the 25 milliliters and then do the 1,000-to-1, but mentally they don't, the AP people aren't looking for that step conversion between milliliters and liters usually. You can kind of do that one in your head and start your track. Now that I've started my track, I can diagonal down my liters. So 1 liter equals a certain amount of moles. and that would be this concentration here, using the molarity as the conversion factor. So 0.350 moles per 1 liter of the sodium hydroxide. Now, because I'm going from here to here, I have to switch compounds. So 1 mole of my sodium hydroxide is going to equate to 1 mole of my hydrochloric acid. And then from there, because I do know the molarity of this, 0.100 moles per 1 liter of my hydrochloric acid, I can use it as a conversion factor and flip it. So I put the moles down here and the liters up here. So the 1 goes on the top and the 0.1 over here goes on the bottom. Now everything is set up to cancel, and we can just do our straight up calculation. So let's cancel liters, moles of sodium hydroxide, moles of the NaOH, moles of the hydrochloric, moles of the hydrochloric cancel, and we end up with liters. Now, once you calculate this, you end up getting 0.0875 liters, which is fine, but we don't usually represent amounts in our burettes in terms of liters because those are in milliliters. So I would multiply it by 1,000 mentally and make it 87.5 milliliters, although it doesn't say you have to put it in milliliters. So either one would be a correct answer. Now, the question posed was using, it's not really M1V1 equals M2V2. That's not really the equation here. This is the dilution equation. You could technically use the modified one where it's NA, MA, VA equals MB, MB, VB. But you have to look at the moles of the acid and the base because, like I said, it's not always 1-to-1. So if you have different moles here. Now, for our purposes and for AP purposes, it's so much better to just do it the stoichiometric way. Because you'll be able to move on and do other things in a much quicker fashion for reactions. So I would always, and this does not work at all for weak acid-base equilibrium. So I would not use this version. I would stick with stoichiometry and really learn how to do it from a stoichiometric perspective, because later on in the weak acid-base equilibrium section, it's going to be much harder if you're going from this and then trying to move back over into regular stoichiometry. So I would say no to this. Don't do it. Don't use it right now. Yes, it works for strong. Don't forget that you have to consider the moles though too. It's not just the straight up dilution equation. And people get it wrong. They'll get it wrong if they're not considering it, especially with ones that are diprotic or have 2 hydroxides in the reaction. So good question. Definitely is an approach for doing strong, but I would highly recommend that you follow stoichiometry because it'll be much more beneficial, especially in the future. Now looking at this particular one too, we need to do calculations for the amount of water in grams and the concentration of the excess. So either the excess is hydrogen or the excess is hydroxide. We don't know which one it is. We kind of have to figure that out. And if you look here, we have the acid and we have amounts for the base here. So when we have both like this, this turns into a limiting reactant problem. So we have to work both of them. Okay, so going to go ahead and work them both to the moles of water. You could technically work it to grams of water too. That's another method that works. But like I said, a lot of times it is an advantage to have the moles because they usually make you go there first anyways. Need the balanced reaction though between our nitric acid and our potassium hydroxide. So let's go ahead and put that out here. Nitric acid plus potassium hydroxide In this particular case, as you can see, one hydroxide, one hydrogen. This one's going to end up being 1-to-1, so we're going to get water out of it. And potassium nitrate would be the salt in this particular case. And it is a soluble salt, so it would stay aqueous. It would not precipitate out. So everything's 1-to-1. That's good to know. Now we can start and do our other tracks. So let's go ahead and do nitric. I'll do nitric in a color, and then I will do the other one in a different color. Let's go with red. So once again, you can use the molarity equation, but like I said, stoichiometry, it's much better to put it in the T-chart. It flows faster. So we have our milliliters. I'm changing it to liters. 1, 2, 3, move it over, change it to liters. Remember, it's just a division by 1,000 in order to do that. Diagonal down the liters, put the moles up here. Now I can use this as a conversion factor. 0.250 moles equals 1 liter for my nitric acid. Now I can work to moles of my water. So over here, working to my moles of my water, it's a 1-to-1 relationship. So 1 mole of my nitric equals 1 mole of my water. I could go ahead and calculate that right now. 0.028 times 0.25. That gives me 0.00700 moles of water. Going to go ahead and do my other one. Work it to moles, and then we can go from there as needed. Purple. Let's do purple. All right, so we have 53 milliliters. Once again, move it over 1, 2, 3. Change that to liters. Yeah, I'm going to get to the grams in just a second. You can go directly to grams if you want to, but I'm going to show you here. Going to moles, diagonal down your liters. 1 liter goes to 1 mole of the KOH here. Oops, not KOOH. Too many O's there. OH, and here is our molarity, so 0.320. Now the stoichiometry part of it, 1 mole KOH equals 1 mole of water. And yes, you know, you would need to represent and show the mole ratio, even though it is 1-to-1. That's part of the work, so make sure you do that. So here are our moles, 0.01696, which I would probably change over to keep 1, 2, 3. I would round that one up, so 0.0170 moles of water. Now, looking here, I can definitely determine which one's my theoretical. Which one would I need to change over to grams? Which one ends up being my theoretical? How do I know out of my 2 possible product numbers which one's my theoretical yield that I would need to go to finish the calculation for grams? The 0.007, because it's less. Yes, the product that comes out the least amount is your theoretical yield. So this is the one I need to convert over, and I can easily do that because 1 mole of water is equivalent to 18.02 grams of water. Probably have that one memorized by now, which you should. So we multiply those out, and I end up getting, here, I'll write it down here, 0.126 grams of water. All right, so that's all good. Got the one thing. We checked that off. We got the grams. All done. Now we got to do the second part here. Figuring out which one's in excess, and we have to figure out its concentration. So which ion, is it hydrogen or hydroxide, is going to be in excess here? And how do I know? Which one's the excess one? Is it the acid or the base? The base is definitely an excess. The one that produced the smaller number amount, this one's the limiting reactant because it produced a smaller amount. This one produced a bigger number, so this one's going to be your excess. So we need to focus on finding the hydroxide. Now we need concentration. So remember, concentration is moles over liters, so we're going to need both of those values. But for right now, we're going to concentrate on finding the moles of hydroxide that's extra. And there are multiple ways that you can do this, but for this particular problem, the easiest way to go is to take your two yields and subtract them. So we have our 0.0170 moles. This is of water, subtracting the other moles of the water. 0.00700. And this is going to give us basically the difference in terms of water, what is extra or left over. So this ends up being 0.0100. So this is moles of water that's extra between the two of them as the product. So that's what I start with over here. I start with that extra amount, moles of water. And now I'm going to go ahead and take this and I'm going to work it to hydroxide. So I'm going to just take this and work it over here to hydroxide. Stoichiometry. So 1 mole of water is equivalent to 1 mole of KOH. And then 1 mole of KOH is equivalent to 1 mole of the hydroxide in the KOH. So as you can see, it ends up being 0.0100 moles of hydroxide. But do show the relationship. I know that it comes out to be a silly number that way, but this would be the quickest, easiest way to figure out the moles of hydroxide that would be extra still floating around in solution. The last thing that we need, of course, is the liters. And what do I need to consider now about the volume? What has happened to our volume up here? Yes, we've added, we have the 28 plus the 53. Okay, so now we have 81 milliliters of solution. So remember, you divide it by the new volume because we're talking about solution concentration. So divide it by the new volume. I'm just going to move it over 1, 2, 3, like so. So 0.018 liters. There's a 0 in there too, but and then when you divide this out, you should get 0.123 molar of hydroxide. Just going to check it real quick, but I'm pretty sure that's what we should get. Yes. So this would be the concentration extra still floating around in the beaker of the hydroxide. If you don't like this way, you can still start with the limiting reactant and you can work it to the excess and then subtract it from the excess original moles. But to me, that's like 3 separate calculations than 1 track. If I just do the difference, start with the track, doesn't take as long, but you're welcome to do it that way. It still works. Limiting to excess and then subtract it from the excess original amount, starting amount. And you could find the moles that way as well. Now titrations. A couple things about titrations. Using a standard solution or titrant to determine the concentration of an unknown, the analyte, or one that you're analyzing. You could say you're analyzing, you want to make sure that this is the correct concentration, so you just do some testing on it. Doesn't necessarily always have to be an unknown, but remember in the Beer's Law lab, we were dealing with the unknown concentration of the brass sample, so we called it the analyte because that was the one we were analyzing. Same kind of term here. The titrant, or the standardized solution, a solution of an acid or base with a known concentration, that's in the burette. Usually you put the known in the burette and you put the analyte or the unknown in the flask or the beaker. Now I've seen it reverse sometimes, but that's the normal procedure I've always seen. You always put the known in the burette for the measuring and you put the unknown in the flask, although I guess it simply wouldn't matter too much in terms of the calculations. So the unknown usually, or the one you're analyzing, would be considered the analyte. The titrant, of course, is the one that you're using, with the standardized solution, the one that you made up, that you know the exact concentration for. That one's always called the titrant. Okay? Some basic terms of acid-base titrations. Now we're going to look at titration curves and what do they look like and what are these graphs about, because you're going to see them. Titration curve are these like S-shaped graphs, sometimes the reverse S-shaped graphs, depending on what we're starting with. But a titration curve is the plot of the pH of the analyte versus the standardized solution being added. So pH is always on the Y, the volume of the sodium hydroxide, or the known in this case is the sodium hydroxide, the titrant. That goes across the X. And then you see this nice little S-shaped curve. The pH, originally low, and then it starts to steadily increase, but this is pretty flat, and then all of a sudden it shoots up. And there's this middle, like, steep inflection point. So this example is showing the titration of hydrochloric with the standard of sodium hydroxide, and as it's showing here, hits this inflection point. But let's look at a more exact titration graph, titration curve. This one is more exact, okay, because it's showing you the milliliters at which the inflection point happens, and they're also showing you the exact pH here. And what you should see, this is noted as the equivalence point. And on a strong, this is a strong acid being titrated by a strong base, the equivalence point should always be 7. The pH of the equivalence point should always be 7. Why is that? Because if all of the hydrogen has been neutralized by the hydroxide, at this point, the only thing besides your spectators that should be in there is water. So if it's pure water, the pH would be 7 at that point. Okay? So the equivalence point, pH 7, okay? Note that, definitely note that that is for a strong acid, strong base titration. The pH always ends up being 7 because that's based off of the idea that at that particular point, pure water would be the only thing left there besides the spectator ions. Now it's this inflection of the titration curve. It's a steep part, and usually you can go right to the middle on a strong, and that of course would be come over here to being your 7 on the y-axis. This is a good example. It starts out very slow, and it does increase a little bit, but then all of a sudden it shoots up, and then at this point you're at 7. But if you keep adding base, then of course the pH continues to go up and it starts to level off at a higher of 13. Now you remember the pH scale, like 7 is neutral, below 7 is acidic, above 7 would be basic, that kind of stuff. For the regular realm of knowing acids and bases. This one is showing a strong base, strong acid titration. So you're taking a strong base and you're titrating with a strong acid. It's pretty much the same thing as the other one, except for the S has been flipped. You're starting at a higher pH, and you're going to keep adding the acid, and it's going to slowly start to do, and then all of a sudden you hit the inflection point, it goes dramatically down. Middle of it would still be 7, pH of 7, pure water. And then you keep adding acid, obviously it's going to continue to decrease down here in the lower pHs and level off at this point. And this is where you measure, if you know your concentration, you measure your volume, then you can figure out the moles. And then you can use those moles to figure out how much is in the unknown. So the equivalence point, what is it in terms of actual, like, math calculation terms? Yes, it's a pH of 7 for strong, strong. But in math calculation terms, it's where the moles of the hydrogen are equivalent to the moles of the hydroxide, because we're getting pure water out. And that's what's important, because if I know the moles of the hydrogen at the equivalence point, I always know the moles of the hydroxide at the equivalence point. So it's exact. And I can use that in stoichiometry to figure out my concentration of my unknown. And that's pretty much what we use it for. So it's the stoichiometric point where the moles equal the moles. And that would be what we would want to know for our definition there. The endpoint is slightly different. Now, of course, we want our endpoint to be the same as our equivalence point, but that's not necessarily always the case. Marks the end of the titration when the indicator changes color. The indicator is an added compound, of course, that changes color at certain pHs. We'll go over that in just a second. But you pick an indicator that's going to change colors around your equivalence point. And you do so to make sure that it's really close so you know when to stop your titration. When you know to mark when it changed color, because that would be your equivalence point, and that's where you want to use your calculations from. So it's not necessarily exactly the same, but it's when the indicator changes color. Now it's your job to pick an appropriate indicator for the equivalence point that you're aiming for. Now, if you're titrating a strong with a strong, you want to hit it right around pH of 7. So you'd want to pick an indicator that changes color around a pH of 7. Now, for the weak acid stuff, that one's a different story. They have different varying equivalence points. So we would look at different pH indicators for ones that involve weak acids and weak bases. So color changes color at different pHs. Let's talk about a few of them. Like a main one that we use all the time is called phenolphthalein. And it's pink when it's a base, and when it's an acid, it's clear. It's a simple either or, and it changes around a pH of 8. So it's just a little bit past that 7. So a lot of people use phenolphthalein for a strong combination. Okay. So this is a good one that they use because it's right around that 7 mark. This one, methyl orange, and it changes more at a lower pH. It's yellow on the more of the basic side, red more on the acidic side. So you would want to use this one at a lower pH. You'll see it on the big picture scale ones that I have for you in just a minute. This is one that I like to use quite a lot, bromothymol blue, because it's like yellow and blue make green. And it's yellow over here in the acidic section. And it's blue over here in the base section. And then right around 7, it does the green. It's like flashes green for just a second. You have to be paying very close attention too, so you don't go past it and add too much. But as you can see, right around 7, it's going to go to this green color, and then it changes over to blue if you go past that. Bromothymol blue is a good one for a strong combination where you're trying to change colors around 7. Now here's just ones showing a bunch of different, ones. Like I said, the methyl orange here, this one changes around a pH of 4, as you can see, red to orange to yellow. But there are varying ones at different pHs depending upon where you're trying to indicate or what you're trying to measure. Would you pick the appropriate indicator for that pH range? And there are way more than just these ones on this chart. You can find a lot of other ones out there that different labs, of course, would use as different way of telling different pHs of certain solutions. So this is just a sample. There's plenty more different types of indicators out there. We usually stick with bromothymol blue, phenolphthalein. In our particular, those are the ones that we have back in the lab. We have a couple other indicators, but use basically those basic ones. And we also have pH meters, which we can just read the pH because we have those that measure using the Logger Pro. So the pH meters are a tad bit more exact, obviously, than using the indicators. Although the indicators are quite pretty, I like to, have them in there just because it's an added extra fun color change. Redox reactions. They're known as oxidation reduction reactions. That's where we get the redox part, where we're talking about transferring electrons. One or more electrons is transferred here. And trying to get my pen to work here. Right, there we go. One or more electrons is transferred during the reaction. Now this involves most reactions. Most reactions fall under the redox category. You may not realize that because we didn't really talk about reactions last year in terms of redox. So let's take a look at an example and let me show you what that means. So here we have our normal reaction of sodium and chlorine. Sodium metal over here, Na, is the solid. Here's the chlorine gas, okay, and it's going to produce the NaCl solid over here, which we like to put on our food and preserve things with. The regular sodium metal is very reactive. We know chlorine gas is pretty toxic and horrible, so you wouldn't want to breathe that in, but produces a very useful product that we like to use. Now, typically, two elements being added together to make one product, that would fall under the synthesis category. That's where we would put it. Synthesis, decomp, combustion. There's double replacement, single replacement, neutralization. You remember all those types of reactions. Well, most of those are all redox as well, or they fall under the redox category. The only one that doesn't would be double replacement, and that's because the oxidation states really don't change. But if we're looking here at this example, and yes, balancing wise, that would be a 2, and this would be a 2 over here. But regular elemental stuff, whether it's diatomic or monatomic, because we have a diatomic one here, monatomic here, both in their elemental states, though, where they haven't gained or lost any electrons, their oxidation states are 0. They're neutral, assigned there. But when we combine them over here and they form the ionic compound, the sodium becomes a plus, the chlorine becomes a -1, +1, -1. So these ones over here do have charges in the compound. Remember, the ionic compound, the charges are supposed to add up to 0. But if you look here, the sodium is going to go from a 0 over here to +1. That means it lost an electron in the process, 0 to +1. If the chlorine goes over here to chloride, which is also a 0, and actually in this case you would two chlorine atoms or would produce 2 chloride ions, but 0 to -1, that means it gained an electron in the process. Anyway, it's gained an electron, okay? So this one is oxidized, this one is reduced in the process of this reaction. One typical basic reaction that's really, falls into the redox. Now we're going to get into more complicated redox where they take place in acidic and basic solutions and you got a lot of other things going on there, but this is like the basic idea of why most reactions are going to fall under redox, because their charges or their assigned oxidation states are going to change from the reactants to the products when they break and form new bonds. So let's define some terms first, and then we'll start worrying about how to assign oxidation states. How to remember: oxidation is loss, reduction is gain. You can use the oil rig to help you remember. That's the one I was taught. That's the one that I use. However, I did come across this in my many studies of chemistry. Leo the lion says grr. And you're welcome to use Leo the lion says grr. Hey, loss of electrons is oxidation, gain of electrons is reduction. Either one is a great way to remember the system. Some other terms, of course, transferring of electrons. This is redox characteristics. Oxidation is an increase in oxidation state. Increase in oxidation state means you're becoming more positive. If you're becoming more positive, you're losing electrons because electrons in and of themselves are negatively charged. A decrease in oxidation state means you're gaining electrons because your oxidation number is getting lower. You're adding negatives to it. It's becoming more negative. So that's what we mean by decrease in oxidation state. The oxidation state is the number assigned to the atom representing the degree of loss of electrons. So once again, don't have to be an ionic compound and have a full charge in order to be assigned an oxidation state. Plenty of covalent and nonmetals get assigned oxidation states in various compounds. This is just a way, like a tally of keeping track of electrons. That's what we're doing here. Now the oxidizing agent and reducing agents, okay, they're kind of the opposite. So if I'm the element being oxidized and I'm losing electrons because it's a partnership, that means I'm causing another element to gain those electrons. So if I'm being oxidized, then I would be the reducing agent. Okay? If I'm being reduced, means I'm gaining electrons. That means I'm taking them away from another element. Therefore, if I'm being reduced, I would be the oxidizing agent because I'm causing the oxidation on the other element. So it's kind of a reversed deal. Now, we also look at the agents in terms of the reactant involved. The agents are always the reactant involved that contains the element that's either, like for the reducing agent, it would be the element being oxidized. It'd be the reactant that has that element in it would be considered the reducing agent. Also, the reactant that had the element being reduced, would look at the entire reactant. The one that has that would be the oxidizing agent. Assigning oxidation numbers. This is a good list, and I'm going to show you some other tricks to the trade. This is a good way to start. Oxidation state of an atom in an element is 0. Like I showed you with sodium and the chlorine, the diatomic, monatomic element is always 0 because you haven't gained or lost electrons at that point. Oxidation state of the monatomic ion. Like for instance, potassium is in group 1, alkali metals, and we know all the alkali metals have a charge of +1 because they lose 1 electron. Their oxidation number is always going to be +1. Now, if you're looking at one of the transition metals, like say, it's iron 3, we know in this particular case it lost 3 electrons. The oxidation state for iron 3, of course, would be +3, as opposed to iron 2, which would be +2. So depending upon which multiple oxidation metal you're talking about, you have to look at the charge on it to figure out its oxidation state. Now, assigning oxidation for monatomic, so say even if you have like a covalent compound, like let's go with like SCl2 here. Both are nonmetals. So in the case where you have nonmetals like this, you need to look at the second one. The second one's going to follow its normal anion oxidation number. And since chlorine is a halogen, and if it's acting as an anion there, it's always going to be -1. I would assign this a -1 here. There are 2 of them, and then of course that adds up to -2. And then here, that means the sulfur's got to be a +2 because it has to add up to 0. That's this one. Sum of the oxidation states in compounds must add up to 0. So we'll go through a few examples of this kind where you use the second atom and you go based off of its normal anion oxidation number to figure out the rest. Another thing to point out, oxygen for our purposes is pretty much going to be -2 no matter what. Except for in peroxides, yes, occasionally peroxide, because peroxide is O2 -2. That means each O is really worth a -1 in that particular case, but that would be a very rare exception. Hydrogen, +1 when it's with all nonmetals. That's why I say covalent compounds. It's only -1 if it's in a hydride. So like NaH like this with a metal, this is when it's acting as a hydride and it would be -1. But if it's like in ammonia like this, all nonmetals, it gets the plus. It gets the +1 idea there. Fluorine is always -1. Now, a lot of the nonmetals have varying oxidation numbers too, depending on where they're located in the compound. That's why I said it's a little bit tricky. But fluorine, no matter what, always is -1. And summing them up, 0 in compounds and sum of oxidations for the charge on the ion. So like for instance, if I have phosphate, this polyatomic ion on phosphate, it must add up to -3 in this particular case because that would be the charge on the overall ion. All right, let's do a few practice problems before we call it a day. All right, finding the oxidation states for all of these elements. So I'm going to start with this very difficult one over here because it's, wow, got a lot of stuff in there, and K2Cr2O7. That's potassium with a certain polyatomic ion. Does anybody remember what Cr2O7 happens to be? It's okay if you don't, but I would check out that polyatomic ion list so you can familiarize yourself. Yes, it's dichromate. Some of you learned your polyatomics well. And if you don't remember dichromate, it carries a charge of -2 in and of itself. But if I'm looking at this particular compound, I'm going to write it over here and kind of spread it out a little bit. Which ones do I know off of my list? I automatically know that oxygen's -2 here because it's not in a peroxide. I also know that K is going to be a +1 because it's an alkali metal and they're always +1s. So I can figure out these guys. Now chromium's one of those multiple oxidation metals, so I really don't know what that one is. I have to calculate and figure it out. In this particular case, this would be -14 because there's 7 times 2. Now remember, this all has to add up to 0, plus something here for the chromiums, plus 1 times 2, so this is a +2 coming out of the potassiums, like so. Now, what do the chromiums have to add up to then? If 2 plus the -14 equals 0, what do the chromiums charge have to add up to? This has to add up to 12. Now remember, there's 2 of them here, so what is each chromium's oxidation state worth? Yes, this is a +6. Very good. So that's how I would figure out for this particular type of example. Now, say, looking here at the polyatomic ion, this is carbonate. If I was doing carbonate, same kind of thing here, except for it adds up to -2 now because we have a charge on here. Oxygen is still -2 in and of itself, so this is a -6. The carbon, though, okay, what does the carbon have to be there to make this equal -2? This is a +4. Don't forget the plus, because you have to indicate plus or minus on all of your oxidation states. So this would be a +4, and the oxygen would be a -2. Let's do one more before we go. Let's take a look at the PCl5. PCl5. Both are nonmetals. Once again, they're both nonmetals like this, and I don't know where to start. I always look at the back part of the molecule and go with, oh, chlorine here. If it's in the back position, it's going to follow its normal anion. What is the normal anion for chlorine? -1. Good. So this is -1. So this adds up to -5. So in this particular case, what must the phosphorus be? What charge or oxidation state is it carrying for this particular compound? It is a +5. So that's how you have to practice assigning oxidation states. We'll come back and do some more practice in the next lesson as we finish out the redox notes.